Okay guys, this is problem number 467. For this one, we're going to calculate the activation energy for this reaction. Some of the more important things to note is the rate constant at 700 Kelvin is going to be 6.2 times 10 to the negative 4, and that's of course the minute minus 1. Our half-life at 760 Kelvin is going to be 29.0 minutes. Okay, just sorry for that right there. But we're going to go ahead and start off. And just remember to find our K. It's going to equal 0.693 divided by half-life. Okay? And then, so we're going to find that. We're going to use this. And we're going to find our rate constant. Right? Okay. And that's going to be at 760 Kelvin. And that's going to equal, remember, the 0.693, and then divided by the half-life, which they give us up here, which is 29. So that's going to be divided by 29. And then this is going to equal, at the very end, 23.89 times 10 to the negative 3. Okay, so that's that one. And that's for our first K1. And then our rate constant at 700, they already gave it to us. Okay, remember it's right up here, and that's going to equal the 6.2 times 10 to the negative 4. Now what we're using these two equations for is for the Arrhenius equation. In case you don't know that equation, it's going to be K equal to the A times the E, and that's going to be all raised to the activation energy, negative EA, divided by the gas constant times T. That's the equation for Arrhenius, okay? Just remember that. Little important. And then you could actually change that to actually equal the log of K1 divided by K2, and then it's going to equal the same negative EA divided by R, and then of course T. Okay, so that's the other way you could write it. So where we're going to be using that, remember we found our K's. This is going to be my K1, my K1, and this is going to equal my K2. Okay, and so we're actually going to be using that, so let's go ahead and do it. So the ln of K1, which is 23.89 times 10 to the negative 3, divided by the K2, which is 6.2 times 10 to the negative 4. Okay, and then of course we're going to equal that to our, well, let's just figure this out. This first is going to be, if we do the equation, and then we calculate, it's going to be 3.65, okay? So then we're going to go and plug that in. So 3.65 is going to equal the negative EA divided by the R. And then to find our temperature, of course, that's actually going to just go ahead and be the 1.278 times 10 to the negative 4. Okay, and the way I got that answer is going to be because it's 1 divided by 760 minus the 1 divided by 700. Okay, that's this right here. Okay, just so you know. And then all that together, we're going to find our EA. And so our EA is going to equal 3.65 times 8.314. Okay. That's our gas constant, in case you didn't know. And then we're going to divide all of that by the temperature that we got, 1.278 times 10 to the negative 4. And that's going to equal, if you put it in the calculator, it's going to be 26.9 times 10 to the negative 4 joules. But we're going to make that kilojoules, that's what they're asking for us, and that's just going to be 0.269 kilojoules. or of course as they have it, 2.7.